All right, so this set of Lewis structures are ones that are exceptions to the octet rule. In other words, they're not going to have 8 valence electrons when they bond. So we can actually divide these into 2 sets. In one set, we have elements that when they bond are going to have less than 8 valence electrons. And it's important to note that these 2 elements we're going to talk about in this section always behave this way. All right, so the first one we're going to look at is boron. So boron is in group 13 on the periodic table. So if we subtract 10, this tells me that boron has 3 valence electrons. And that's all it has to bond with. So what this means is that boron is only going to have 3 bonds. And remember that each bond represents a total of 2 electrons being shared. So when boron's finished bonding, it will have just 6 electrons instead of 8. So let's look at what this looks like. So we could have BH3 and boron, since there's only one atom of boron, that would make it our central atom. And it would have 3 hydrogens surrounding it. And remember, we can draw this one of 2 ways. So we can draw them with the dashes between the 2 elements representing bonds. So it would look like this. Again, remember that hydrogen only can bond once, and because it only has 1 valence electron, so hydrogen should never have unshared electrons around it. The other way to draw this is using dots. And we can show that boron has 3 electrons, 1, 2, 3, and hydrogen each has 1. So there's 1 for this hydrogen, there's 1 for this hydrogen, and 1 for that hydrogen. So the 2 ways we can draw boron. All right, let's look at the next element. So beryllium is in group 2, so it only has 2 valence electrons. And so this means that when beryllium bonds, it will only be able to form 2 bonds. And if each bond is made up of 2 electrons, it will have just 4 valence electrons instead of the 8. Okay. All right, and we can draw an example by looking at BeCl3. So beryllium would be my central atom. And we would put 2 chlorines surrounding it. And again, we can use dashes to represent my 2 bonds. So there's beryllium's electrons. Now chlorine has 7 electrons, 1 in a bond. So that means that there are 6 remaining. And we can show those as lone pairs. We can also show this same Lewis structure with using dots instead of dashes. Okay, so chlorine has 7, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then beryllium has 2. Okay, so those are my exceptions that always behave this way. So you will need to memorize those. Okay, and then let's look at another set of exceptions. So the other set of exceptions we're going to look at are ones that have an expanded valence, okay, which means that they're going to have more than 8 electrons. And what gives them ability to do this is that they have d orbitals that they can use for bonding. Now, the important part to remember about these elements is that you always want to see if they can obey the octet rule first, and then decide if they need an expanded valence. So for this reason, these elements do not always behave this way. And so there's 2 elements we're going to look at. We're going to look at phosphorus, and phosphorus is in group 15 of the periodic table. So it has, if we subtract 10, it has 5 valence electrons to bond with. So this means it would be able to form 5 bonds. And if each bond is made up of 2 electrons, it would have the ability to have 10 electrons instead of 8. Now, the best example for me to describe how you know that it's going to behave this way is it has to be bonding to 5 atoms, like we're going to see in our example. So since there's only 1 phosphorus, we make that the central atom. And we're going to put 5 chlorine surrounding it. And again, we can use dashes to represent my 5 bonds, or you can use dots. Now, phosphorus has 5 valence electrons, and we can see from my dot picture that all 5 are involved in bonding. Chlorine has 7 valence electrons, and so 1's in the bond, so that means the other 6, all have to be represented as lone pairs. All right, and the second example of our exception is sulfur. So sulfur is in group 16. If I subtract 10, it gives me 6 valence electrons. And so in this case, sulfur has 6 bonds. And if each bond has 2 electrons, sulfur would be having 12 electrons instead of 8. And again, not always going to behave this way. And the best way to figure that out is that it has to be able to bond to 6 atoms. All right, so let's look at my Lewis structures for these. So here's sulfur. It's my central atom because I only have 1. And here are my 6 fluorines. And you can draw it with the lines that represent 2 electrons, or we can draw it with dots. Nope. And sulfur has 6 electrons. 1, 2, 3, 4, 5, 6. And then the fluorines have 7. So 1 in the bond, and that leaves 6 remaining. So that means it's going to have 3 lone pairs around each fluorine. All right, so phosphorus and sulfur are my 2 examples where we can have more than 8 valence electrons, along with an example to look at how the bonds form.